Hello everyone, my name is Kiran and today I'll be speaking about the Super Cameo Candy Detector. So let's first understand what Super Cameo Candy Detector is. So it's the world's largest imaging water Cherenkov detector at Kamioka village in Japan. So this is a detector which is able to detect the neutrinos. And neutrinos are the particles which are very less interactive. They are because they are chargeless as well as they are massless particles. So it's very difficult to detect neutrinos. So this is the detector which can detect neutrinos. So it's able to detect neutrinos with energies between a few million electron volt and a few giga electron volt. It is built under a mountain to ensure that the neutrinos are not drowned by their particles. It means that neutrinos are the particles that do not interact with anything. They pass straight through everything, every material, and that is why they are built under a mountain so that any other particle which are coming with the neutrinos, they cannot reach to such depth. Only the neutrinos reach there so that they can be detected easily. So Super K detector discovered the neutrino oscillations, and this discovery got the second Nobel Prizes. So basically neutrino oscillation is a phenomena of the oscillations which prove that neutrinos had some small non-zero mass, and that is why this discovery got the Nobel Prize. And also the presence of these small mass of the neutrinos also led to the theory that there is some different theory beyond the standard model. So let's first understand what neutrinos are. Neutrinos are the particles which are chargeless as well as the massless particles. They travels with the speed of light. That means they are very fast particles, and since they don't have any charge and mass, so they do not interact with anything. And we know that for the detection of any particle, we definitely need that the particle has to interact with something so that we can detect it. But the interaction probability of these neutrinos is very small. That is 1 in 10 trillion particles. So, what is the interaction mechanism of these neutrinos? These neutrinos interact via the weak forces. So, yeah, neutrinos are produced from the nuclear power stations, particle accelerators, birth and collisions, and death of the stars, and particularly the explosion of supernovas. So, let's see this super K detector. Okay, as we can see that this super K detector is built underground, and this is built under, it is placed 1000 meter underground, and these small dots that we can see are the photomultiplier tubes which are 11,000 in number, and this area between the this area is filled with the 50,000 tons of water. So we can see that this is how our super K detector looks inside. This is filled with 50,000 tons of water, and these are the photomultiplier tubes. So the height of this tank is 42.2 meter in height and around 36 meter in diameter, and this building is a 10-story high building. So let's now see the photomultiplier tubes. So these are the photomultiplier tubes which are embedded within the super key detector. So these are around 11,000, which are of the diameter of 50 centimeter, and these looks like the giant light bulbs. And the sensitivity of these photomultiplier tubes which are used inside the detector is such that they can even spot a candle on the moon. So let's first understand the mechanism of working of photomultiplier tubes. So photomultiplier tubes has the photocathodes inside it and the diodes which are provided with the potential difference. So whenever a light is incident on these photomultiplier tubes, the photons interact with the photocathode and emit the electrons. These electrons now goes to the diodes which are provided with the potential difference, and by the secondary emission on the diodes, these electrons gets multiplied in the number, so increasing the number of counts or the events so that even a small light can be detected by these photomultiplier tubes. So these photomultiplier tubes are not actually orange colored, they are reflecting the color of the sodium lamp that is used inside these photomultiplier tubes, and inside these photomultiplier tubes there is highly vacuum. So let's see how these neutrinos are detected, because we are seeing that these are the chargeless as well as the massless particles, and they are very fast, they move with the speed of light. So there must be at least some phenomena by which they are interacting so that we can detect them. So let's understand how these neutrinos detect. So neutrinos interact via the weak interactions. Uh, so whenever a neutrino comes near the nucleus of an atom, this neutrino emit the W or Z bosons. So whenever it comes near the vicinity of the nucleus, it under the influence of the nucleus, it emits the bosons, and these bosons are the very heavy particles which are around 100 times the mass of the protons. Now these bosons, which goes to the nucleus and breaks it apart and creates all the sorts of water particles. Now we can see that these bosons, whenever they go to any nucleus, they break that nucleus and create the particles like protons and neutrons from the energy of collision. Because there is a collision, so because of that energy of collision, particles, charged particles like protons and uncharged particles like neutrons and other particles are created. These particles now fly by the atoms in the detector. The created particles fly by the atoms in detectors and create the secondary interactions. These particles create the secondary interactions which make the electrical signals that can be detected. So this is the phenomena of the detection of neutrinos. So let's now try to understand the working of the super K detector. So super K detector is basically a Cherenkov detector, and in this the neutrino smashes into water and create the charged particles. So the charged particles which are created by these interactions in water will emit the Cherenkov light. So let's try to understand what is the Cherenkov radiations. So whenever a charged particle which is moving at a speed faster than the speed of light moves through a medium, the light is emitted and that light is known as a Cherenkov light. So basically what happens is that whenever a charged particle which is moving at a very high speed is creating a field of its own, and whenever this field is created, this field is disrupting other particles which are in the vicinity of this charged particle. So this happens because the field of these charged particles. Yeah. So this field affects the other particles which are present in the vicinity of these charged particles. Due to the effect of these field, there will be the transitions of electromagnetic radiations, so that these particles would come back to their initial state. And because of those electromagnetic transitions of the radiations, there would be light produced, and this light would be known as the Cherenkov light. And this Cherenkov light is produced in the form of the cones, and by studying the rings of the cones we can estimate about the energy of the incident neutrino. So similarly in our super K detector, the neutrino is coming and it is interacting with water, and when it interact with water, it gets converted into electrons and muons, which are the charged particles, and they do not travel very far. Now these charged particles would create the electromagnetic field of their own, and because of this electromagnetic field, the this electromagnetic field would affect the other molecules, which will give rise to the Cherenkov radiations, and these Cherenkov radiations would make rings inside the detector. And now using the size of these rings and the time that light takes to arrive at the detector's energy in the trajectory of the parent neutrino is decided. So now that we have understand that what actually happens in the super K detector is that a neutrino comes, it interacts with water and decays into the muons and electrons, and these muons and electrons gives rise to these cones and the cones of the Cherenkov radiations. And studying these cones of the Cherenkov radiations using the sensitive photomultiplier tubes, we can estimate the energy of these incident neutrinos. So basically this is the working of our super K detector. So let's come to the summary part. So what are the results from the super K experiment? So the super K experiment started in 1996 with the aim of resolving the neutrino problems. So initially the experiment was started to resolve the neutrino problems, the solar neutrino puzzle and the atmospheric neutrino anomaly. And the discovery of the neutrino oscillations was announced in 1998. This was a very important discovery because this led to the fact that neutrino has some small mass, because initially it was assumed that these neutrinos are the massless particles, but actually it was found that they have small mass, and that led to the theory that there could be something beyond the standard model that we are using till date. But what are the drawbacks of these super K detector that we need to improve it? that neither proton decay nor another neutrino burst from supernova were not observed from the last 23 years of the operations. Uh, Actually, the Super K detector was initially started to study the proton decay, but till 23 years of its operation, we are not able to detect the proton decay or any other neutrino burst from the supernova. And the continuous operation of the Super K detector may find some solution to the remaining problems, but the size of the Super K detector is a limiting fact that we cannot discover some of the properties that we want to find out. So let's understand some history about the Super K detector, like how it was discovered, how it was started, and what was its initial steps. So initially in 1982, there was a project that named Cameo Candy was funded. So initially there was a detector that was Cameo Candy only, and it was a detector which was having 2,000 tons of water and 1,000 PMTs. So the prior aim of this detector was to conduct an extensive search for the proton decay. And so initially we can see that there was not the aim of neutrino. The initial aim, the prior aim was to conduct an extensive search for the proton decay. But after a few months, the electrons observed from muon decay down to 15 million electron volt. So it was thought that some improvements could be done to this detector so that we can detect the energies up to 10 million electron volt. So there was a proposal that we should try to improve some things in these Cameo Candy detector. So in 1991, when the Super K got approved, neutrino astronomy, solar neutrinos, supernova neutrinos, and proton decay were the top listed subjects. So after improvements, these were the subjects that were uh, that were put forward so that to be discovered by using the Super K detector. So in 1996, this Super K detector was constructed. And what are the future aims after this Super K detector? So the future aims are to spot the decay of the protons that we haven't see yet. And the second aim is the adding gadolinium to water to make it more sensitive to stray neutrinos. So gadolinium is basically an element which can produce scintillations or X-rays. Like it is sensitive to the radiations, and we can add it to water so that it can become even more sensitive, so that we can discover the stray neutrinos as well. And the third aim is to differentiate between antineutrinos and neutrinos. So basically antineutrinos are the antiparticles of neutrinos, and there is no such difference that can differentiate these particles as well as antiparticles, because there is no difference of mass, no charge, and not any such difference that can be seen between these particles. So the aim is to see that what is the difference between these particle and antiparticles. So a bigger project which is even 5 times larger than this Super K, known as the Hyper K detector, started in 2010, in which 13 countries are involved, and its construction got approved in December 2009. So Hyper Cameo Candy detector is a neutrino observatory which is 20 times larger than the tank of a Super K detector. It is even 20 times larger than Super K, which will be having billion liters of ultra pure water, having larger number of sensors. And the tank for the Super K detector will be a double cylinder, which is 2 into 250 meters long and approximately 14 to 40 meters, and this is buried 650 meters deep, and so that we can reduce the interference from the cosmic radiations. So that's all about the Hyper Cameo Candy and Super Cameo Candy detector. Thank you.